Good morning, all. Thank you for joining us. Just to be aligned, 15 minutes is nothing, and we can't teach no one how to irrigate in 15 minutes. So I'm not even going to try. What I'm going to do, as Lior explained, I'm going to give you some tips that hopefully will be good for you and will help you to grow better in your Soilless substrates. So, as time is very limited, let's just dive into the water. Soilless substrate is the most efficient growing method, no doubt for that. We have optimal water availability and aeration. Now, water and air ratio are critical, and I will explain it later. We also have optimal nutrient concentration, and I'm not going to talk about it because Ofer has a full presentation on that. Just for the reference, if we are looking on tomato yields in kilograms per 1 cubic meter of water, we can see that if we're going in open field, we'll be around average of 17 kilos of tomatoes for 1 cubic meter of water. But if we're going to unheated plastic greenhouse, it will be almost double. We're around 30 kilos for 1 cubic meter. And it's increasing until around 70 kilos if we're going to what we're calling high-tech greenhouses. So no doubt, Soilless substrate is the most efficient growing method. But like in life, we have also some risks and some challenges. Today, I'm going to speak about 3 main challenges in growing in Soilless substrates. First one, low buffer. The second one, substrate salination. And the last one, water distribution. So, for the first challenge, low buffer. In this table, we can see the amount of water in liters that the roots can sense in different scenarios. So, in the first line, we can see that if we are growing tomatoes in soil, roots can sense about 150 liters of water. While when growing in container, 25 liters container in this example, with coco peat, the roots will sense around 12 liters of water. So this is 10 times less. Now, the challenge is clear. If the capacity of the container is limited, also the option of the roots to fill the water is limited. I like to call it the motorcycle paradox. Why the motorcycle paradox? If you're taking a scooter and a sport motorcycle, both have the same functionality. They both can bring you to the same point. The main difference is in the speed or quality in our case, and the damage or the potential damage in case of if something goes wrong, in case of accident. Same goes here. If you're growing tomatoes in soil, and from some reason you can't irrigate for 1 or 2 days, probably nothing will happen. But if you're growing in Soilless media and you will not irrigate for 1 or 2 days during the summer, you should expect big troubles. Okay, so we understand low buffer is a problem and we need to treat it. Did you know that you're mostly paying for pore space when buying a bag of Soilless substrate? Only 15 to 50% of Soilless substrate volume are solids, while the rest is pore space. This pore space can be filled by water or by air. Wide pores are good for air exchange, while narrow pores hold the water. They're doing it thanks to the capillarity forces. I will explain later. So in the table above, we can see a few kinds of substrates and different characters. For example, we can see that coco coir have total porosity, total pore space of 85%, with 55% water holding capacity and 30% air volume. While volcanic ash, for example, have only 60% of total porosity, with 40% of water holding capacity and only 20% of air volume. Now, I guess most of you know what is water holding capacity, but just in case, water holding capacity is defined as the percentage of total pore space that is occupied by water after drainage is completed from the substrate. In other words, this is the ability of the substrate to hold water. Okay, I guess most of you knew that substrate type have a crucial influence on water holding capacity. But I'm not sure everybody knows that also container configuration have an influence on water holding capacity. In the left side, we can see the different ratios between air and water in different heights or in different layers of the container. So we can see, for example, that in the upper layer, we have 43% of air with only 7% of water. And when we are going down to the low layer, we can see that we don't have air at all. We have only water. Some volume of the soil at the bottom of the container never drains. This is due to relatively less influence of gravity on substrate water in this zone. What does it mean? For a given diameter, shorter containers will hold a greater portion of water and therefore less air. This is critical, so I'll repeat it again. For a given diameter, shorter containers will hold a greater portion of water and therefore less air. So my first tip, choose the right combination of substrate type and container configuration. Note, optimal air volume is between 20 to 25%. So when you work with shallow containers, like in the picture, make sure to choose substrate with high air capacity. Second tip, use pulse irrigation and do it right. What is pulse irrigation? Pulse irrigation is an irrigation method that utilizes frequent irrigations with shorter duration. Okay, as I told you before, the volume of the volume of the substrate is very limited when we're working in containers. So if we irrigate the full amount of water once, all the water will drain down. We need to use pulse irrigation. Number of pulses will be affected mainly by your substrate water holding capacity that we've just talked about it. Very important, don't let your substrate to get dry between irrigation, as it may create an air pocket. Once you have an air pocket, it will be very hard to wet it again. So keep it wet all the time. Use CNL drippers to ensure high uniformity all around the plot or the field. Abed will have a full presentation on that later, so I will let him talk about it. Tip number 3, sense the substrate. You can look at the sun to know the time, but you prefer to use a watch, right? Same here. Why guessing when it comes to water content? Feel it, sense it. Use sensors. We have a few options. Option number 1, use a moisture sensor. We recommend on delta T or Netacap. Delta T is a moisture sensor, very accurate, very easy to install, but it measures the moisture sensor only in one point in the container. Netacap is a new sensor that can measure the moisture content in few points, 2 or 3, depends on the length, and it also can measure temperature in your container. The second option is to use a scale to monitor the substrate weight. How does it work? Very simply. This weight measures all the time the weight of the container, of the substrate, and of the plant. And then you can see the changes along the day, and you can understand how much water the plant uses and how much you need to irrigate. Each system has its advantages and disadvantages. Sensors, moisture sensors are relatively more cheap, so you can use more of them. The main problem with sensors is that they are measuring the moisture content only in a very specific place or point in your container. The scale is usually a bit more expensive, but it gives you an average, and then you have a better look. And of course, the best option is to use a combination of both of them. You can use the scale and the moisture sensors. Okay, for the next challenge, prevent substrate salination. So we all know that irrigation water contains salts in different levels, depends on the quality of the water. Fertilizers also contain salts. High salt concentration may harm the plants and may even kill them. Very short irrigation may not be enough to push the salts out of the root area. So tip number 4, minimum irrigation duration should be not less than 2 minutes. Work with low flow drippers to extend each pulse to minimum of 2 minutes. In this illustration, we can see in the left side of the illustration, we can see what happens when we are using a high flow dripper. So water goes straight down without pushing the salts from the root zone. And in the right side, we can see what happens when we're working with low flow, in this case with 0.5 liter per hour. So the water are going slowly, thanks to capillarity. They are going to the sides and pushing the salts out of the root zone. Tip number 5, monitor your drainage. Drainage is a tool. This is not a goal. This is very important. Many times when I'm speaking with people, they're telling me I'm irrigating 40% drainage. Why? I don't know, because someone told me that this is what I should do. So no, drainage is there to make sure you don't accumulate salt in your substrate. Okay, this is the only reason why we're irrigating with more water than the plant needs. How much more? It depends. You need to know what you're doing. Daily measurements of EC level, they are must. Okay, you need to measure the EC in the dripper and in the drain. Then you have to look on the delta between the EC in and EC out, the EC in the dripper and the EC in the drain. If the delta is smaller than one point, you are fine. If it's higher than 1 point, you have some unbalanced process and you need to fix it. Once you're familiar with your substrate, with the plants, with the water and fertilizer characters, you may use a drainage volume as a supporting tool for irrigation. Very important. When you're planning your irrigation system, don't forget to plan a drainage measurement system. Many times we are coming to a new greenhouse and we're asking the grower, how do you think to measure the drainage? And then silent, because nobody remembered to tell him that he need to measure the drainage. So when you're planning a new project, keep it in mind all the time that you need to measure the drainage. Challenge number 3, and the last one for today, water distribution. Gravity is stronger than capillarity. If I haven't said it yet, gravity is the force that takes water from top to bottom. Capillarity is the forces that take water to the side and from bottom up. Root exists only where water is present. No water, no roots. Remember it. No water, no roots. When space is limited, roots are aspiring to use any available space for growth. So tip number 6, spread the water on top as wide as possible. Because as I explained to you, the gravity is strong. So you need to spread the water from top. Tip number 7, use multiple water outlets. Okay, even if we can give the whole amount with one dripper, just for the example, if this plant, this blueberry plant in the picture, need 4 liters per day, we can put one dripper of 4 liters and give all the water at once. But then all the water will drain down. No, use few water outlets. Okay, so a quick recap. Challenge number 1, low buffer. Challenge number 2, substrate salination. Challenge number 3, water distribution. Tip number 1, choose the right combination of substrate type and container configuration. Tip number 2, use pulse irrigation and do it right. Tip number 3, sense the substrate, use sensors. Tip number 4, minimum length for irrigation should be not less than 2 minutes. Tip number 5, monitor the drainage. Tip number 6, spread the water on top as wide as possible. And tip number 7, use multiple water outlets. That's all from my side. I hope it was useful for you. And we're going straight to the next speaker, Ofer Halperin.
Hello, my name is Ofer Halperin, and in my short presentation, I will give you a short brief on irrigation in soilless media. So I will go, first of all, over the agenda. I will start with the basic concept of soilless fertigation. We'll talk briefly on the pH adjustments, fertigation monitoring, and fertilizer and stock solution preparation for soilless media. So first of all, we need to understand what are the differences between soil and soilless media fertigation. And all the differences comes from the fact that in soilless, like Roy mentioned before, we are talking about small root volume. The growing media is inert, not like in the soil. And so the nutrient and pH buffer capacity of the medium is very low and limited. Therefore, we need to understand that we need to supply to the plant all the time the full package of nutrients and include microelements and calcium in order to prevent some deficiency. And we need to monitor and be aware all the time for the pH and the EC of of the solution. Also, we need to use the right amount, the right products, let's say low ammonium without urea, in order to prevent some problems that we'll discuss later on. This is why in soil grown we are working quantitative, we are talking about kilograms per hectare, while in Soilless we work in proportional. When I'm talking proportional fertigation, what I mean that in Soilless we are working in concentration and not in quantities. And the concept is supply the plant the ideal nutrient solution for optimal nutrient uptake. We are talking about the right nutrient ratios and concentration, and the optimal EC and pH for the right on optimal and maximum growth of the plant. And of course, all the time, constant monitoring of the drainage, of the substrate, the climate, and the plant response. So there are two approaches when we are talking about proportional fertigation, and both of them are talking about concentration, but one is millimole and one is ppm, and I will explain briefly the difference between two approaches, and it doesn't really matter whatever approach you prefer to work. They're both the same, but it's important to understand what is the difference. And a short flashback to your chemistry lessons from high school. What is a millimole? Mole is a quantity of elements. In order to unify the number of particles of each element, we are taking the same number, and this is it's a big number mole, but we are talking about the same number because different particles or different elements have different weight. So the same number of particles will weight differently, and this is what we are calling molar mass. Just for example, if we are looking on 1 mole of calcium, potassium, magnesium, or ammonium, we have the same number of particles, but the weight of each element will be different. It will be 40 or 39 if we are talking about calcium, or 24 and 17 if you're talking to ammonium. So, and why it's important? Let's ask a questions. If I'm fertigating my substrate, my tomato plant with 250 ppm of potassium or 100 ppm of nitrogen, what if I'm the plant root, what I see more in my solution, more nitrogen or more potassium? Well, if I'm taking the ppm, which is milligram per liter, and I'm converting it into millimole, into particles, this is the factors that you see. I need to divide by 14 or by 39, which is the molar mass, as we discussed. And the answer is that 250 ppm of potassium is equal to 6.4 millimole per liter, while 100 ppm of nitrogen is equal to 8.6 millimole. So the plant root actually fills more particles of nitrogen than potassium in the atmosphere. So, and the plant's roots is working not in mass, they're working in particles. They need to exchange one particle of nitrogen, one ions, in exchange to hydrogen or hydroxide. So this is why it's so important that then millimole is talking in the language of the roots, and we need to understand it. Another short flashback for your chemistry lessons in high school. If we are talking about fertilizers, the inorganic fertilizers are salts. When salt is dissolved in water, it's separated to anions and cations, negatively charged and positively charged ions. When we are talking about the cations, we are talking in the solution about ammonium, potassium, calcium, magnesium, and sodium, while the anions are nitrate, phosphorus, sulfur, and chloride. Why it is important? We need to understand and remember that the nutrients or the ions are not alone in the solution. They are together, all of them, and they interact all the time between one to another. And it can be it's defined very nicely in the chart below. On the right, it's called mother chart, and it's described the interactions between the different nutrients in the soil solution. You can have the positive effect or the negative effect, which means that one element can increase or decrease the availability of other element, depends on many parameters. When we are talking about soilless, the big influence is the electric charge. This is why when we are talking about cations, you can see here that potassium, calcium, and magnesium have a negative effect on each other. They are antagonists one to each other. It means that when I'm increasing the amount of potassium in my nutrient solution, I can affect or negatively affect on calcium and magnesium availability for the plant. Therefore, sometimes you can have calcium deficiency in the plant only because you increase the ratio of the potassium. So this is very important to understand when you are changing your nutrient solution, to understand what can be the effects and to react accordingly. Another very important parameter for the availability of nutrients is the pH. You can see here in the chart on the right that each nutrient has a different availability with respect to the pH of the soil solution. Let's say there are nutrients that are more available in acidic atmosphere or in some in neutral or alkaline atmosphere. This is why we need to supply the pH for the optimal range in order to optimize our uptake for all the micro, and secondary elements. If the pH will be too high, will affect the availability, let's say, of the micro elements. Well, if the pH, and also will have the risk of precipitation of calcium and phosphorus. Well, when the pH is too low, it's too acidic for the plant roots, unless we are talking about blueberries. And also it can affect the substrate, and the availability of NPK, calcium, and magnesium will be reduced. So this is why we want to maintain an optimal pH of around 5.8 to 6.2. This is the optimal range for fertigation in soilless substrate. And how we are doing it, we are using acids in order to reduce the pH of the nutrient solution to the desired range. But sometimes we are trying and we are struggling to reach the target pH, and the pH unit is not stable and not reaching the desired target range. This is usually because we have a high bicarbonate level in the water. Bicarbonate is creating a buffer for pH reduction, and you can see here on the chart, when we have high bicarbonate in the water, the pH is high, and I'm adding more and more acids, but the pH is more or less remains stable until I'm reaching around 60 ppm of bicarbonate, and only from then I can see the decrease in the pH. This is why we recommend to use, possible to use acid, but to do the titration of the bicarbonate as a pre-treatment or to use the right pH unit in order to reduce the amount to around 30 to 60 ppm, and only afterwards to give the pH unit the time to do the fine tuning in line. How can I know how much acid I need to add to in order to neutralize the bicarbonate? We have two common practices. The first one is calculation. Do the chemistry. You know how much bicarbonate you have. You know what is the specifications of your acid, the source, the concentration, the density, and you can estimate how much acid you need to add to the water in order to neutralize the bicarbonate and reduce the buffer capacity of the water. The other method is more simple and more accurate because there are also another influencer on the pH. It's a bucket titration. Just take water, your irrigation water, record the pH level, add acid, and all the time measure the water pH, and then until you are reaching the full titration curve, and then you know how much acid you need to add to your specific water in order to reach the target pH. What you need to remember is that acids, especially if you are using nitric acid or phosphoric acid, also contribute nutrients to the solution. Nitric is nitrate and phosphoric is P2O5. So you need to take it into consideration when you are calculating your fertilization recipe. So, okay, I got everything. I know what I need to do. I'm working with ppm. I'm changing my recipe according to the plant development every 14 or every period. And now I feel that I'm ready to go. And this is only the starting point. After we are starting, like Ray mentioned, all the time we need to monitor and sense our plant and our substrate and our drain. Like Roy mentioned in the previous presentation, all the time I need to do analysis and measurements of the EC and the pH. Roy mentioned about with respect to salinity, and also we have irrigation. We can change and adjust our irrigation according to the drainage. But if we are talking about fertigation, and the delta EC is too high than expected, and of course, and after we are dealing with the irrigation protocol and make it work optimal, we can change the EC of the target EC of the nutrient solution in order to avoid salinity or to waste fertilizers. The drainage pH, if we are monitoring it and we see that in the drainage we are with outside the range that we want to be for the target pH, then we can adjust the nitrate and the ammonium ratio in order to increase or decrease the pH of the root zone. So it's very important that drainage monitoring is a fundamental practice in soilless media for irrigation and for fertigation. The second step of correction according to drainage analysis is to take from time to time a full analysis of the nutrients in the solution. The different nutrients there you can detect then you can detect the ratio and a specific deficiency or excess of one of the nutrients. And as you can see here in the table for guidelines of the difference in the drainage compared to the dripper, then you can see that the calcium and magnesium concentration in the drainage should be higher than in the dripper, while potassium, phosphorus, nitrogen, and sulfur should be similar or slightly lower than the dripper concentration. Anyhow, if you see that you are out of those boundaries, you should adjust your nutrient solution by 10–20% and monitor again, test again in order to see that you got the right response from the plant and from the substrate. So, okay, I know what I need to do. I'm monitoring and feel very confident. And what I need to understand and remember that this is very accurate atmosphere. So this is why I need to work with the right fertilizer, right source. And it's very important also to work with high quality of fertilizers. Let's say if I'm talking about the nitrogen source, we discussed before that we want to limit our ammonium concentration. So this is why most of the time we are working on nitrate-based fertilizers. 80–90% of the nitrogen should come from nitrate. Also, urea is not allowed for soilless media. And the nitrate can come most of the time from calcium nitrate, potassium nitrate, and magnesium nitrate. The phosphorus, we are not using most of the time NAP because it contains ammonium, so the preferred phosphate source is monopotassium phosphate, MKP, which supply potassium, and the additional potassium is we are working also in chloride-free products. We don't want the chloride to accumulate and to influence to increase the salinity. So this is why SOP, potassium sulfate or potassium nitrate, are the preferred sources for potassium. And because we also want the nitrate, so the dominant potassium source in soilless is potassium nitrate. Calcium nitrate, this is the king for calcium in soilless media. And magnesium, you have two options. You have magnesium nitrate and magnesium sulfate. Usually the magnesium sulfate is more economic, and also it supplies sulfate and not additional nitrates that sometimes you don't need more nitrates. So most of the time people are working with magnesium sulfate. Of course, it depends on your water, on your nutrient solution. Microelements, it's very essential to give the full package. And if we are working in rock wool, then you don't need to work chelates and only for the iron. And in cocoa and other organic substrates, it's preferred to work with chelates, usually EDTA. This is the most common chelate for soilless media. Last object, I want to talk a little bit about tank mix, how much fertilizer I need to apply, what kind of fertilizer I need to put in what tank, and how to adjust our injection. This is a different topic, but we need to take into consideration the dosing unit spec, the number of tank, the tank volume, the injector working range, the solubility of the fertilizers and the water temperature, the compatibility between fertilizers. You can't mix potassium, phosphorus with calcium, for example, and the type of fertilizers. You need to understand what is the full package of the fertilizer in order to know in what tank to put it. So I just want to go briefly on fertilizer solubility. The solubility of fertilizer it means that how much fertilizers I can add in the solution in order to how many kilogram in 1 liter in 1 cubic meter of water I can add without getting any precipitation. So of course it depends on the fertilizer type and characteristic, and also it depends on the water temperature and the quality of the fertilizers. Here is a very general table. It gives you general guidelines how much fertilizers you can add in the different water temperature. And of course, if you have low quality fertilizer, the solubility usually is lower than high quality fertilizer. And you need to understand that when you are mixing more than one fertilizers, the solubility is the solubility of both fertilizers. So I suggest do it in small scale in a bucket. See that you don't have precipitation before you are dissolving the full tank of fertilizers. If we are optimizing our stock solution, we can reduce our operation, minimize the number of preparation, and just save labor. So let me summarize the nutrient principle in soilless media. First of all, we need to determine the nutrient requirement for plant growth according to plant development status. We need to determine the correct concentration ratio between the various elements. We need to adjust and control our pH, our salinity and EC, work with the right products, and all the time monitor and react. Thank you very much, and I hope this presentation was beneficial, and we'll go to the next slide.
Okay, so we'll dive into details quickly, because I think that it's very limited in time, and we would need to cover a lot of things. So as you understood from the two previous presentations, the solution for working on soilless substrate in order to be able to reach the full potential is working by pulse irrigation, what we call precision irrigation. So what is the typical irrigation system? Normally, in these systems, people are irrigating a little bit more than the system can absorb. And the main reason for that is what Roy mentioned in his previous presentation, is the concentration between air and water inside the soil. As you remember, in some of these substrates, you can see that there are higher concentration of water in the bottom of the soil, less on the top of the soil. So people, what they do normally in order to increase the soil moisture in the upper level of the soil, they actually increase their irrigation in order to be able to create a better and uniform environment for the roots. This is becoming common in irrigation system, especially on soilless culture. And this actually dictates the reason that people today are irrigation based on drain measurement. That means the drain becomes part of the irrigation consideration when people work with soilless culture. So pulse irrigation is an approach to utilize more frequent irrigation with shorter durations. The objective of pulse irrigation is actually to match the application rate for the irrigation system with the absorption rate of the substrate by applying these cycles that I've mentioned before. This allows better absorption of water and nutrients that apply to the soil. Now, I've tried here to explain that a little bit in graphics so you'll understand it. And I can tell you that pulse irrigation, it's considered to be something that we can even increase the frequency on that. So if pulse irrigation people were used to work on 7 pulses per day or 11 pulses per day, it depends in the end of the day on your irrigation cycle and irrigation volume, but it can be increased towards 30, and crazy can do it even 200 cycles per day. So we call it pulse irrigation, and those that take it to that level of 200 pulses per day, we call it kind of nano irrigation. So if I try to explain that, so if the y-axis describes the soil moisture within the soil and the x-axis describes the time, so when we give this frequent irrigation, there's always a trigger when we start the irrigation. I can say that in most protected crops, this trigger is the radiation sum. In many cases, it can be soil moisture. In other cases, it can be time. That means I can decide when I should start irrigation. And based on that, I do the measurement of the drainage. And based on that, I correct my irrigation. Same thing can be with radiation sum. So there is an algorithm that exists in our automation system and many others also, that you can start the irrigation based on measurement of the soil moisture or on time or on radiation sum that you have predetermined that, start the irrigation cycle, measure the drainage based on that, fix it. There's an algorithm, there is a graph that fixes. So this determines the number of irrigation cycles. But if I want to be as much as possible accurate and be in an optimum conditions for root growth, I need to give more and more irrigation. That means more frequent irrigation. The more frequent irrigation I'm giving, the less drainage I'm creating. As Ofer mentioned, drainage is not a target. Drainage is a tool that helps us actually optimize our irrigation. It's not the target that I need to work with 40 irrigation, as Roy mentioned. It is not something that is target, okay? These, I would say, numbers that are given in the industry, 30% drainage or 40% drainage, is just because of what I'm mentioning over here, okay? Because common practices, people came to the point that they understood, okay, 30% or 40% drainage is giving them this best optimal condition. But in the end of the day, it all depends on many aspects, as Ray mentioned, the volume of your substrate, the type of the substrate that you're using, and many aspects. So then take that as a guideline. So drainage is not a target, it's just a tool, okay? So that's the way. Now, another thing that I'm going to say over here is something probably you will hear that and you will be a little bit confused. I'm saying when we are talking about soilless substrate, uniformity of water and quantity in many cases is more important than water quality. You know, when we're talking about drip, we are always talking about water quality and clogging resistance of drippers and so on. Here, you need to consider that uniformity is critical and you don't want to play with this issue, okay? And I'm giving you an example so you will understand what I'm talking about. If we take a field of 10 hectares that can have 200,000 of drippers, let's take any type of crop that you're talking about. Let's say take blueberry that have 100,000 pots per hectare. And you need to give 30 irrigation cycles per day. And each cycle is 0.1 liter per each pot, which means 100 cc. It is comparable to 6 million cups of coffee. That means 6 million shots of coffee that you need to do on one day. And here we need to give the same quality of coffee every time with very high accuracy. So this is a big challenge. And that's the reason that you saw before that there was a solution that Roy mentioned that in his presentation, which is using the right product, which is using the CNL, which I'm going to relate to that very soon. So this is something that is very critical to understand. Uniformity, when we're talking about soilless substrate, is the most critical, and this is the most thing that we need to consider and we need to target, okay? If we talk about standard irrigation system, in regular irrigation system, this is the way that the irrigation system looks like. We start with the filling of the system, then the irrigation, then the emptying. Now, if you consider if we are working in hours, for example, so it takes me like a certain amount of minutes to fill the system, depends on the system volume at the end of the day, and then the time for irrigation, then the time for emptying until the next irrigation cycle. As you remember, Roy mentioned in his presentation, 2 minutes. Now, you need to consider if it takes me 5 minutes to fill the system, so what is 2 minutes here? So we cannot rely on the same, I would say, design criteria that we know from the past from standard drip irrigation system. So it's taking us to a totally different place. That's the reason that we need to start using something that was called the advancement time of the system. That means the time it takes the water and nutrients to reach to the last dripper in your field, okay? And this is called the advancement time of the system. There are formulas for calculating that, but we have in our irrigation handbook, we have the tables that you can use these tables and you can understand what would be the time or the advancement time that we already pre-calculated for you. You'll be able at least to roughly estimate what would be the advancement time in your field. And here I'm going to give you an example, okay? For example, this field is a field of a greenhouse, which is about 9 hectares. That is divided into 8 valve sections. The dripper in this case is 3 liters per hour, spacing 27.7, which gives capacity of 1.68 meters per hour, okay, liters per square meter per hour, okay? So this is just an example of a system. Now let's look at this system and try to estimate the volume that is in this system, okay? If we take this system and look at the volume, so you will see that we have 7,000 liters in the main pipe, 1,000 liters in the connection pipe. On the crossover, we have 16,000 meters. In the dripper line, which is the biggest one, will be about 36,000 liters. So there's a volume of 65 cubic that we need to fill in every irrigation cycle. That means if the system drains, you need to understand, every time that I need to fill the system, I need to fill 65 cubic before the system starts irrigating. So that's something that we cannot live with if we want to irrigate in 2 minutes or 3 minutes or 4 minutes. This is something that cannot work, and that's the reason that we need to keep the system full all the time. Otherwise, we'll need every time to refill the system, and that's something that we cannot allow. Now, let's take an example for the same greenhouse over here. If we were working standard without the feature that we are going to use, which will not drain the system. So you can see here that the first 5 minutes will be filling the line and then the sub mains, and it will take me about 30 minutes to be able to fill this 9. And you understand that it cannot work. If we want you to irrigate 2 minutes, this cannot work. So that's the reason that we need to work with system that's all the time full. And when I'm giving a trigger to irrigate, it will start irrigating immediately. What could be the implications of filling the system? So first, a slow, long-lasting reduction in EC and pH. You understand why this could happen. And long-term response to change in fertilizer recipe. If you see that you need to change, you remember what the Offer mentioned, if we need to change the recipe in order to match the EC and pH level that we need to do, so that system will not be able to respond on time. So that's the reason that this is very critical. Larger differences in delivery and short-time irrigation intervals. This is something that is critical. In many cases, we go to the field and we see people that says, okay, the first dripper and the last dripper is not giving the same flow rate. It doesn't mean that there is a problem with the dripper. In most cases, there's a problem with the system design. That means there was a leakage in the system, and this leakage caused the system to empty. The system was not full. So before the last dripper started dripping, the first dripper was dripping before it, and the last dripper was waiting until the pipe will be full. So that creates this flow variation. And if my time is short, and it's 2 minutes or 3 minutes, then that's actually create this difference. So if there is a 1 minute even difference between the first dripper and the last dripper, so there is 30% flow variation between the first dripper and the last dripper, and that's actually create the biggest problem. So in this case, we understand these are the problems and these are the consequences of these problems. So what can be the solution? The solution, as I mentioned before, in standard irrigation system, we always try to work with bigger volume to reduce head losses. You understand, if I'm running the same flow rate in the system, the bigger pipe, the less head losses. The smaller the pipe, the higher head losses. And when we are talking about soilless culture, when we are talking about protected crop greenhouses, we need here to kind of give away a little bit on the head losses and prefer to work on smaller diameter system and dripper line. And for sure, the most important thing is using CNL system. What is CNL? CNL is coming from compensated non-leakage. Other companies call it anti-drainage. Other companies call it AD from anti-drainage. But this is what we call the system that does not allow the water to drain from it. Okay. Now, the CNL function always exists on pressure compensated dripper. It does not exist in non-PC drippers. This actually utilizes the pressure compensation mechanism to create this phenomena of drainage. Okay, it exists in almost all of Netafim pressure compensated drippers. And here you can see some of our products in this portfolio, which is PCJ, which is pressure compensated junior dripper, or PC Online, or Uniram. All of these drippers have this ability of being CNL, which means ability of being non-drainage. And by using this product, you can actually guarantee that the system does not empty from the water. And in this case, when you operate the system on the next cycle, it always will be full with water and start immediately. I will give you a little bit. How do we realize what is anti-drainage? Here is an example of a dripper line that exists in a greenhouse. Normally, there is a 1% slope because anyway, this is what you have in your soil. And if you define the system, let's say the lateral length is 140 meters in this case, and if you define a system that have a CNL function, that have a shutoff pressure, and I will explain what is shutoff pressure, of 1.4 meter, when I close the valve, this 140 meter will be full with water and will be ready for the next irrigation cycle. So it never empties. And that's critical. That's the reason it's very important that we understand what is shutoff pressure in CNL functions. Okay, so shutoff pressure is actually the pressure in which the system, when you shut off the main valve, the system does not drain, okay, or stop leaking. Okay, how do we measure shutoff pressure? It's easy. You can actually take any transparent pipe, you can connect it to the beginning of your dripper line, you shut off the main valve and let the system drain. And after the system finishes draining, you look at the height of this column. And the height of this column determines what is the shutoff pressure of the system. So it's very important. There are different shutoff pressure for the different components, either online dripper or inline dripper or even non-leakage valve. So there is always a lot of levels of shutoff pressure, and that actually determines the pressure in which the system shut off. In our products, we have two levels of shutoff pressure, CNL and high CNL. The CNL is the standard one. High CNL is allowing you actually to work on shutoff pressure on slopy topography. So that means it's not only the pressure that's created in the system because of head losses, it's also the pressure that's created in the system also because of slopy areas. Okay, so we take just a few examples in our products. For example, in Uniram, we have in the standard product, we have 1.4 meter shutoff pressure, and on the high CNL, we have 2.5 meter shutoff pressure. If we go to PC, we have 1.5 meter on the standard one and 3 on the high CNL. If we go to PCJ, we have 1.2 versus 1.8 on the shutoff pressure. So the shutoff pressure is the pressure that determines the pressure in which the system stops leaking. Okay, so another component which is very important to be used also when we're talking about design of irrigation system is what we call DNL, which is dripper line non-leakage device. This is a device that is added on the beginning of the dripper line, okay, and stops drainage from the dripper line to the submain. Okay, it's not only stopping the drainage from the drippers itself, it also sometimes you have drainage between the dripper line and the submain. Sometimes it's due to connection leakages, sometimes to mismatches, sometimes probably a hole that's created. So you need to stop that from happening. So we have a DNL, and also in the DNL, we have these issues of shutoff pressure. So we have different level of shutoff pressure on DNLs, which determines the pressure in which the dripper line shut off. Now, why is there a need for different shutoff pressure? Because different shutoff pressure dictates also the pressure regulation range that we have on the product, either on the valve or on the dripper line itself. So that's the reason that we need number of these to be able to determine different shutoff pressures. Okay. Now, as you can see over here, we have different types, and each type is colored by a different color coding, and we have it from 2 meters up to 8 meters. Okay. Now, there is a lot of design consideration. I'm giving here just main guidelines on design consideration. When you are using dripper or dripper line, always use excess pressure at the inlet of the system. In dripper line, we use 20% more and on DNLs we use 30% more. So normally, if the system says that if the shutoff is 0.8, use 1 point, not shutoff. Sorry, if the pressure range is 0.8, use 1.1. If it's 1.2, use 1.5, and so on, so on. So these are the design considerations we need to consider while we are designing these systems. An example of how DNL valve could help us, for example, if I'm using a very long lateral and I see that the slope in my greenhouse or in my field is high, like 2%. So after 140 meters, I already reached the shutoff pressure of the dripper line. So every dripper after that will start leaking. So in order to stop that from leaking, I can add another DNL valve in the middle, and that will stop leaking. So every time I'm adding a DNL valve, I'm kind of zeroing the pressure and starting from the beginning. So it allows me going longer laterals. So you can see here the solution. Once we added that, we zero that, and the system actually will remain full, and we can start the next irrigation cycle without a problem. We can do that even not once, we can do that even twice, and that actually allows me doing that in this way. So to summarize, we have different type of DNL valves. Some of them can even be buried under the soil. So this is something that needed to be considered while selecting the DNL valves. That's it. Thank you. And if there will be questions, we'll be more than happy to answer.